This lecture is on nuclear physics. There are many reasons why one should study nuclear physics. Here are some. Why does the sun shine? Why are some atoms stable while others are not? There have been 5 mass extinctions here on Earth. How do we know that this happened? Humans, where does all that stuff that make you come from? In other words, how are atoms made? To answer these questions as well as others, we must go back to the forces of the atom to start to answer them. Forces of the atom. In our last chapter, we looked at the role of the electric force in the atom. Here's what we found. We found that if we had electric forces, there was attractive forces between positive and negative charges, and if we had 2 positive charges or 2 negative charges, these forces were repulsive. Atoms form because of the electrical attraction between electrons and neutrons. So with our quantum model, we have the nucleus, and we have the energy levels where the electrons live in, and the electrons are dictated in these red dots, and these two feel this attractive electrical force. We also learned that surrounding the nucleus was this intense electrical and magnetic force fields, and that any type of electric charge that tried to get close either to the atom or the nucleus would be repelled. Rutherford sent in alpha particles that were deflected by the nucleus. Here we start a discussion on nuclear physics. Chemistry is how electrons rearrange themselves. Nuclear physics is only about the interactions of the neutrons and the protons inside the nucleus. So from now on, we don't care about what the electrons are doing, we only care about the neutrons and protons. Forces of the nucleus. When we look closely at the nucleus, just like when we look closely at atoms, we had an incorrect picture of the atom. Looked at the Rutherford model, we saw that that was a bad model of the atom, where an electron was circling the nucleus. In a very similar situation, in nuclear physics, there's another bad model of the nucleus, but we will use it in the meantime. We have a nuclei that has a boundary, and these red plus ones are going to be a proton, and you'll see me write them P with the plus symbol on top. And then we have these blue ones, which are the neutrons, and they have no charge, so therefore I leave them blank here. When one looks at the electrical forces of the nucleus, there's a big problem. It shouldn't exist. The nucleus is filled with positive protons that are trying to blow it apart. Picture-wise, if I look at my nucleus, I have all these positive red charges. These charges are all trying to push away from each other. So these red arrows are the repulsive electrical forces of all the protons inside the nucleus. The electric force is trying to blow the nucleus apart. But nuclei of atoms are stable for the most part. What do I mean by stable? Stable means that there's at least one stable isotope. Atoms with atomic numbers 1 through 82, that means from hydrogen to lead, are stable and do not radioactively decay. That means that these atoms will last at least 10 times the age of the Earth. Why is the nucleus not blowing apart? Answer: there must be another force that prevents this from happening. This force is called the strong nuclear force. QCD, which stands for quantum chromodynamics, and the strong nuclear force. Protons and neutrons are made of 3 tiny particles called quarks. So if I have a proton or a neutron, and this is the boundary here, then inside are 3 quarks, which I've colored in red, blue, and green. The force that binds these quarks together inside the neutron and proton is called the QCD force. But here's the important piece to the picture. The QCD force extends just outside the outer edge of the neutron and proton. Picture-wise, I imagine a proton or a neutron. Inside is where the quarks interact with this QCD force. But there's a little bit of the QCD force that leaks out beyond the edge of the neutron and the proton. This leaking out is called the strong nuclear force, and that's what binds protons and neutrons. In other words, the strong nuclear force is a residual force. It's the leftovers of the QCD force from inside the neutron and proton. The attractive strong nuclear force binds protons and neutrons together with the exact same strength. That is, if I have two protons close enough to each other, then the proton-proton bond is exact same as the proton-neutron bond, or the neutron-neutron bond. Inside the nucleus, the strong nuclear force does not distinguish between a neutron and a proton. Because of this, it is common for neutrons and protons to be called nucleons. Key point: the attractive strong nuclear force is much stronger than the repulsive electric force due to the protons. The way I write this here is that the force of the strong nuclear force is much stronger than the electrical force. It is for this reason why atoms are stable on the periodic table. That is, atoms 1 through 82, from hydrogen to lead, and are not radioactive. On the other hand, atoms from 83 to 118, 83 is bismuth, are unstable or radioactive and have no stable isotopes. I will explain radioactive in a little bit. Atoms and the band of stability. The balance of protons and neutrons in stable nuclei is beautifully illustrated by plotting the number of neutrons versus the number of protons. This plot is called the band of stability, and it's shown here to the right. Some observations about the band of stability. All stable nuclei are in the black dotted band. Unstable nuclei are in the yellow band. Any nuclei that lies in this gray area do not exist. Nuclei determined by the number of neutrons and by the number of protons, they're plotted vertically for neutrons, horizontally for protons. It is the binding energy that determines whether a nucleus is stable or unstable. What is binding energy? The work done by the attractive strong nuclear force is the binding energy. From the work energy theorem, we could say that when work is done, there's a change in energy. What is this change in energy? Well, that's the binding energy, and the binding energy is a form of potential energy. To explain binding energy, I want to start with an analogy called a potential well. Imagine a well or hole in the ground where a red ball is at the bottom, and the depth here turns out to be proportional to the binding energy. Question: how much energy/work is required to get the red ball out of the well or potential well? Since binding energy is a form of potential energy, it's the amount of potential energy. In other words, I draw a bar diagram for it. So this bar indicates the depth of the well, which is how much work you'd have to do. If I have a smaller potential well, I have a smaller binding energy. Smaller depth, smaller binding energy, easier to remove. If I have a larger depth, then I have a larger binding energy, and therefore it's harder to remove. Let's apply this type of thinking to the nucleus. It's the work of the attractive strong nuclear force that creates the potential well for the neutrons and protons. This binding energy is the glue that keeps neutrons and protons inside the nucleus. Picture-wise, I see a nucleus that has protons and neutrons inside of it. If I was to focus on one proton, that proton is in the bottom of a well. If I was to focus on one neutron, it's in the bottom of a well. And the depth of these wells are the same because the strong nuclear force does not differentiate between protons and neutrons. But the repulsive electric force is working to eject protons out of the nucleus. From the work energy theorem, we can say here that the work by repulsive electric force is equal to this electrical energy. And this is the repulsive electrical energy inside the nucleus. So let's draw a picture of this electrical energy. So if I have less protons in the nucleus, that means that there's less repulsive electrical energy in the nucleus. Therefore, its electrical energy bar is small. But if I have more protons in the nucleus, I have more repulsive electrical energy in the nucleus. Therefore, my bar is bigger for electrical energy. Now we can state when a nucleus is stable or unstable by looking at the binding energy versus the electrical energy contained within the nucleus. Now we can state when a nucleus is stable or unstable. Stable nuclei have binding energies much larger than the electrical repulsive energy. Picture-wise, the blue bar, binding energy, is much bigger than the electrical repulsive energy. These are the elements between 1 to 82, from hydrogen to lead, and these are the black dotted band in the band of stability. So that means one of these isotopes can last 10 times the age of the Earth. Highly unstable nuclei have binding energies that are much less than the electrical energy. Picture-wise, the little binding energy bar is much smaller than the bar for the electrical energy. These elements are between 93 and 118. That means these are the heaviest ones, and none of these exist naturally on Earth. These atoms are in the yellow part of the band, in the band of stability. The last group of atoms that are unstable nuclei have binding energies and electrical energies that are approximately the same. These elements are between 83 and 91. They exist naturally on Earth, but form no stable isotopes, and are also located in the yellow part of the band of stability.